Well, let's record in case this could benefit somebody else. Sure, maybe. Let's see, I get that camera working for that. All right. So I guess I'll share screen. Okay, so what is the homework? Let's see. Is there anything specific about the homework problems?
No, I think it's all just making sense. Just doing more is just helpful.
Okay. So we had a problem like this and a problem like this, and so we could do like examples like that if you'd like. I'm going to talk about more things about the project in the next class, so I could try to invent a problem or problems that are similar to the homework if you'd like.
Yeah, sure.
Okay, so let's try that. All right. We got some weird loaded thing here, and it's I tried to pick out one of the stress concentrations we haven't used yet. One of the issues we'll have when inventing a problem is trying to get it so that it's on the just in the right zone where it's we're going to be able to predict failure. But we'll just go ahead and just pick out numbers. So I think I have Shigley open right here. Oh, look at that, it did. And we'll start by going to some stress concentration things and work backwards maybe from there. So yeah, I haven't. This is the for the homework problem. These are the stress concentration things that you would use, right? And they're a little weird, so that you have to kind of like read through and kind of see that they do this kind of. They're weird compared to some of the other ones that we're having here. But let's. I don't think we've done where we drilled a hole through something, right? Have we used these before?
No, not through shafts.
Okay, so let's do a problem where we do something with these. So that'll be our invented problem. So let me think. It's dangerous stuff. Thinking, and I'll put this over to the side for the time being, and get to my camera and try to invent a problem. All right, so just to keep it straightforward here, I think I actually had this as a homework once, or something like it. So maybe I should pick out an old homework problem here. I could do that, and then I would know that I would get the right answer. So I have crazy methods of saving things. Um, so like I have like homework summaries from other years. So this is homework 11. So I can kind of see what I've done in the past to try to keep track of them. So let's see. Here's an old homework. Here's from fall of 17. Oh, there were two separate ones. That's interesting. Wonder why. No, there's homework 9 and then homework 11. Huh. I guess they're kind of similar. I don't know. Here you go. From homework spring of 2019. So let's zoom in on that one. So we have cool drawn 1045 steel, and the loads are vary from 300 pounds up to 75 pounds down, right? And we have the diameter of this thing is 1 inch. I'm writing all this down as I talk about it. That's why I'm doing it here. Oh, and this happens every 10 seconds. I need to write that word every 10 seconds. And let's see, other parameters that we're going to want to know here. Did I give the dimensions of this? Okay, yeah. Okay, so 1 inch with a 0.25 inch hole drilled in it, and it's 6 inches long. Okay, well, 6 inches to the point where it matters, right there. So, and that little hole in the thing is has a diameter of 0.25 inch diameter. Okay, and we want to find first cycle safety factor, and then the 4 safety factors, and then try to do all the other stuff. So this is pretty similar to problems that we've done before. Let me see. I said spring of 19, so I can peek at my solution. That's fair, right? I don't have to, demonstrate my ability to think on the fly here all the time.
You already did it. I'd say that's fair.
There you go. All right, good. So, first thing I probably want to do is figure out what the stresses are going to be. Yeah, I'm trying to figure out what the hell I just did here. That's a little weird. All right. So, I'll bring my stress concentration thing over here and look. You'll see that for the torsion, let's see, I'll close this down so it makes it bigger. For the torsion, they give us this J over C thing. And they give us, there's actually 2 lines. There's one for A and there's one for B. And you could look real close up here and you can see that B is just to the outside and A is apparently where this is going to be the maximum. But we really care about B because we're going to try to find a spot on here where it has the worst case scenario. That's where the crack is going to initiate, right? So we're going to use the bottom one here of B, and that's dependent on just D over D. That's the only ratio that matters. And we're also going to look, and we need this J over C kind of idea. And they don't quite explain that, but I don't know why they didn't write J over R instead, because that would make more sense, because it's sort of like the equivalent of TR over J. So instead, we're just going to go T over JC, right? So the JC is the thing that we're going to get from that equation that they pasted up here. All right, so I'll write that J over C down is going to be pi d cubed over 16 minus little d times d squared over 6. Similarly, while we're here, we note that they give us a formula for the nominal stress for the bending. So that's going to be sigma 0 m over this large thing that is very similar to the one that we just did, the one for the torque, where it's pi capital D cubed over 32 minus little d times d squared over 6. All right, so those are the first things that I'm going to take care of, or I'm going to do, is to write this, figure out this geometry. So let's see. I'll do the bottom. Go ahead.
Real quick, I'm looking at the figure A1511.
Yep.
And the moment goes like with the direction of the slot. Is there another case for if it's perpendicular to the slot?
It's a good question, but the thing is though, that would be on the hole would be on the neutral axis, so it wouldn't matter.
Okay, gotcha.
Right, because there would be no stress if it was going the other way. It's a good question though. I thought the same thing, and then like had to backtrack and go, oh yeah, that wouldn't matter because there's no stress on the neutral axis.
Okay, so like even if the little d is like somewhat sizable, then it still shouldn't matter.
Well, I mean, it would it definitely would have it cause a stress rising thing there, but I think mostly what we would find is that the moment of inertia would just be reduced, right? The cross section you'd
Okay.
have to you'd have a
Right.
cross section instead that looked like this right here, and that probably is what's going to cause the stress. Yeah, there could be a stress riser like right there, but the most amount of stress is most likely going to be like right up to there. I don't know that Peterson probably has something like that in there. He really did a thorough job of coming up with just about every conceivable scenario
Gotcha.
for
Okay.
stress
Hmm.
risers. And we're just getting like a sampler of that.
Okay. Thank
Um,
you.
no problem. Thanks for asking. D cubed over 32 minus D for 6, so that's just going to be pi, and the big D is 1, and the little d is the 0.25. That's right there, right? And 1 squared over 6. And we get 0.05651, and these are inches cubed. Did I put a torsion on this thing? I can't remember I didn't look my original problem. No, it didn't. Okay, so I didn't actually need all that. I don't know why I put that on there. Never mind. I should have. I should have put some kind of torque onto this. That would make it a more interesting problem. But now, for the time being, we're just going to have one fluctuating thing. Yeah. So ours is a little bit different than this because we would our homework problem, we would have a combination of stresses being placed on there. Maybe I will do that here. I'm going to go ahead and do that, calling an audible. Let's put a torque on here of a constant. Let's see how much I could probably get away with on here. Boom, boom, boom. Yeah, I think we were okay. So I don't know. I'm gonna arbitrarily pick in. I'm gonna go in. This is dangerous. I'm gonna go 1,000 inch-pounds. I don't know what that'll do. So let me actually calculate this stuff. I'm backing up and say I got pi 1 cubed over 16 minus 0.25, and all of this looks pretty much the same right here, except for the 32 versus the 16, and 1 squared over 6. So let's see, we got ourselves, so you can't even see it, right? Pi, oh, no, pi over divided by 16, because that's 1. That's good. And then just 0.25 divided by 6 and subtract. And so I get like 0.1547, right? Yeah, it shouldn't be too much. Yeah, they're close to being one after the other. Okay. And so for my torsion, I am going to get that torque 1,000, right? It's not going to be a lot, is it? Well, okay, 0.1547. All right, so it's not a lot, but 6.465 KSI. Now for this one, okay, and this is going to be a steady, right? So it's a nominal, and this is constant. My bending, on the other hand, the bending is going to change, right? So it's going to alter. So it's going to have a max bending is going to be equal to 300 times the 6, right? So we got 1,800 inch-pounds. And then so that's when it goes upward. So that means that you're going to have compression up here, but tension on the bottom. And then on here, we're going to have, for a given spot, we would have tension on the top for this and compression on the bottom. But let's probably zoom in onto the bottom instead, I think, because otherwise our minimum, this would be a negative, right? So we're going to say this is going to be on the one that causes a tension. It's not, I was going to write tension, but the moment isn't tension. It's a moment that causes tension. And then we'll have the 300 times our 6, and that's going to give us a 450 inch-pounds. Something we should maybe I could say, I could actually turn the moments into a mid-range and an alternating, but I'm going to do it with the stress instead. So I'm going to go with my nominal max, and it's going to be 1800 divided by my 0.05651, and I end up getting 31.85 KSI, and that's going to be in tension. And then I'll go with my min, and so I'm going to get 450.05651, and I'm going to make that the compression one. 400. Whoop, not sorry. So that's 7.963 KSI compression. I can just move the camera. I don't have to move that. Okay. And let's see. So my mid-range nominal is going to be this plus that over 2. But that's 7. That's negative. So I end up with 11.95 KSI. And then I could have the same thing for my alternating, is going to be 31.85 minus 7.963 divided by 2. So I get an alternating of 19.91 KSI. All right, so this is going to be this right here is going to combine with that right there when we go to get my overall mid-range and alternating, right? So the mid-range, I do the mid-range first, right? So we're going to have mid-range here, going to be, I can do this in my head, I swear I can. KF mid-range here squared plus 3 times K. Oh, I haven't looked these up yet. The KF, these stress concentrations. I meant to do that. All right, tau mid-range squared square root. All right, so yeah. So let me look up my KFs, or KTs, I guess I'll start out with. And my mouse is hidden. There it goes. There we go. So, oh, I need my D over D. Well, that's pretty easy because it's 0.25 divided by 1. So, ta-da, not difficult to do. And what I said this was before, well, now I got to do this one first. All right. So that was just 0.25. And I said that was 1.93, which seems very ambitious right there. So I guess I'm going to write it underneath here. I guess I could just write this underneath it. KT is approximately 1.93. While I'm here, and I haven't done this before because I just added this aspect onto the problem to try to make it more applicable to our homework. We want 0.25. I'm going to say, okay, so we have 2.6 right here. So I'm going to say that's 2.7. It's actually probably just a little less than 2.7, I think. But 2.7 is good enough, right? So I'm going to go that my KTS is approximately, did I just say 2.7? My attention span is so short sometimes. Yeah, 2.7. So that's going to actually increase this thing quite a bit. And now I also need to go and find my Qs for my notch sensitivity. So let's see here. I'll open that up over here. Yeah, and we are chapter 6. Notch sensitivity. So okay, so our diameter of the notch is 0.25, so the radius is 0.125. So that's what we're going to use here. We need some material properties though, don't we? We were told it was 1045 cold drawn. You could trust me that if I give you the numbers, they're the right ones. We don't necessarily have to flip to the book. So the yield strength for that is 77 KSI, and the ultimate strength is 91 KSI. So looking back at this, so that was like 91, so it's close to 100, a little bit underneath it. So we have a notch sensitivity floating right around there. So kind of in the mid 0.8s, right? Because this would be 0.9 right there. So yeah, but it's a little bit below this. Let's see, what did I say it was? I said it was 0.834. I must have used an equation. But I'm not gonna for this next one. We'll do this similar thing. And here's our 100 KSI. And yeah, that's actually pretty close to 0.9. No, I guess I'm gonna go actually 0.85. Right, I'll go 0.85 on that one. It wasn't all that much different. So I can get a KF of 1 plus 0.834 times our 1.93 minus 1 here, and 1.93 minus 1 times, I already have this one written out, so I don't know why I'm calculating. It's the other one I have to calculate. This one, it comes out to 1.777. This is the one I have to calculate because I hadn't done it before. 1 plus 0.85 times our 2.7 minus 1. I don't know, too many things. Okay. 0.85 and 1.7 times that, and then add 1 to it. We get 2.445. All right. So, coming back, okay, so that was a thought cloud because it was a diversion. We had to go back up to there. For our mid-range, we're going to get the KF of 1.777 times the mid-range, this guy, 11.95, and that gets inside the square, plus 3, and we go 2.445 and times my where'd you go, this guy up here, right? So this was a nominal because of the twist I arbitrarily put onto the thing. And so now we do have to calculate that. So that's a 6.465 times square it times 3. Okay. And then 11.95 times 1.777, and square that, add them together, take the square root, and it's kind of jumped up there, 34.65 KSI. compared to, okay, so my mid-range before I put the torque in there on the previous homework was 21.22, so this is a increase. But here for the alternating, because the torque was steady, right? I said that this was a constant torque being applied to the thing. So the only alternating stress is this guy times the stress concentration. So I'll put a prime in there, but we don't have to do the thing because it's just the square root of the square of the thing, so it didn't really matter. So we have 1.777 times our 19.91, and we're left with 35.37 KSI. So here's our mid-range and our alternating, and we can start doing some stuff with the fatigue part of it now. With this, we need to get the endurance strength. I'm gonna like fly through that part because we've already kind of had a bit of practice in doing it. It's just being careful that we pick out the right factors and coefficients. And I'm using the values from the 10th edition because I haven't updated them. So we find that SE by taking KA, KB, KC, KD, KE, and KF and SE prime. And as I had mentioned, the limit was 91 KSI. Why is so doesn't want to come on, focus. There you go. Here's something to focus on. There you go. All right. Okay, so here's just what the factors ended up being. 0.817 for the surface condition factor, which I believe I chose because it was cold drawn. I think that's the thing. A lot of times that's my go-tos, the cold drawn and machined, because a lot of the stuff that we deal with is machined. So yeah, it's good. I don't know what the ground one is. I'd like to find out, but it's maybe someday I'll find out. And then for this, it's not rotating and it's round. So I did get a DE for this, right? Where you take 0.37 and you multiply it by the actual diameter, which is a weird thing. I just did something weird. I don't know. Anyway, and my solution, I'm looking at my old solution, which is a typed out, written out a Word document solution. And I made a mistake there. I never caught, but that's okay. So we use that and we stick it back into that KB thing where I think it's 0.879 times the diameter raised to the negative 0.107, right? So we use this diameter inside here and we end up getting a 0.9777. I seem to have seen that one before, actually. I think my combination of stuff. I think it's with a 1-inch shaft diameter. That's what but yeah. Anyway, the C. This is a bending thing. It does have torsion in there, but it doesn't matter. So that's going to be 1 for there, and then the rest are 1s. Put another 1 in there for good measure. And then we have 91 divided by 2, right? That's the SE prime. And we're left with 36.34. I said 36 and I wrote 63. 36.34 KSI. All right, so now we have this SE. We're able to go through and get all of our factors. So our first one is the Langer. And Langer is the yield strength divided by sigma A plus sigma M. Not hard. 77 was the yield, and so I have what, 35.37, but now 34.65. I'm really close, but still, we're still okay. 77 and 35.37, 34.65 plus divided. We're at 1.10. Only 2 decimal places, right? It actually came out to 1.0997, but 1.16. It's close, good enough. Then we're going to go to Soderberg. And that's 1 over sigma A divided by SE plus sigma M divided by SY. So 35.37 divided by 36.34. So it was already pretty close with just the alternating one to being goners. But now we're going to add in the contribution of the steady stress. And that's going to be divided by 77. So we go 35 point, I can't read my own writing, 37 divided by 36.34, boom. And then we have 34.65 divided by 77. And add them together and take the inverse, and we get 0.70. So he's predicting failure. Goodman. One over sigma A over SE plus sigma M over ultimate this time. So not a lot different there, except for that ultimate. So 34.65 and 91. 35.37, 36 point, I can't read that, 34, and 34.65 and 91 divided, add them. So you get 0.74. So really 0.7385. Do I really want to do that? I'll do it. I'm not lazy. I'm not lazy. I'll just keep repeating that, and so I'm not lazy, but I feel lazy. Don't feel like doing it, but I will do it anyway. Gerber. So this is a long one here. Gerb. I don't want to write it out twice. I'll write it out. 1/2 the ultimate divided by the mid-range squared, the alternating divided by the SE, and then -1, I guess it is here, -1 plus, I don't know why we didn't subtract 1 out the other side, that's all right. 1 plus 2 sigma M SE over SUT sigma A, all of u squared, close bracket. My N looks like an H. So 1/2 and 91 divided by 34.65 squared. Sigma A is 35.37, and this is 36.34 minus 1 plus square root 1 plus, and then 2 sigma M is 34.65. SE is 36.34, and ultimate is 91, and sigma A is 35.37. There's a lot of stuff to keep track of. And now this is where the Hewlett-Packard calculator really works in. It's also a strategy. I mean, you know, what do you always do with this strategy of here is you jump into the one that's nested the most. And if you do that from this strategy, you never have to like re-enter in a number. You can just like go bump, 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 bump. It's a much faster way, and people lose time on exams. So it's a learning curve, but it's at the same time you'll find a devoted following, and I have yet to recruit a student. But I think when I do, I still sometimes get in touch with the professor that convinced me to try the Hewlett-Packard calculator, and I will contact her and say, "I got one. I got one. I got a person to go to convert." And she'd be like, "Great, leave me alone." Okay. So I got all that stuff on the inside while I was talking, 35.37. So I probably screwed it up. 36.34 divided. Um, and now we're going to have 91 over 34.65. Divide it and square it and multiply it and divide by 2. And I get 0.91. 0.9053. Like I said, I probably screwed it up, but it kind of makes sense to the way it is. We could take a look at it here in a second. And then let's see, we have the ASME, which is some considerably easier than the Gerber one. But I'm only going to make you calculate the Gerber one once for this homework and then never again. So there you go. It would just be a mean thing to do on an exam because it just takes a lot of time. So this is the sigma A over SE squared plus my sigma M over S. I said sigma. Sigma. Now the yield strength right here. I don't know if anyone at the ASME uses this particular thing, but it's named after them. Must be a reason for it. So we have our alternating is 35.37, and our endurance strength was 36.34 squared, and sigma M that's the new one here, 34.65, because we modified the problem, and that's divided by 77. All right, so let's see. 35.37, 36.34, square them, then 34.65. I really need to write a little neater. And then square them. Okay, so I screwed something up over here. I don't know what happened. All right, so I got to start again. 35.37. This makes for great video, doesn't it? 36.34 divided and squared. Okay, then 34.65, 77 divided and squared. Add the two, flip them, square root them. 0.93. And that makes sense, I guess, especially looking at the older problem. I had a 0.97 here and a 0.99 for there. So I got pretty close. So I think I got probably the math right. So now we have, let's do the life prediction thing first. So we want to get the equivalent completely reversed based on Goodman. So we use the alternating divided by 1 minus the mid-range over the ultimate. And from that, we will get the alternating is 35.37. 1 minus the mid-range is 34.65 over the ultimate, which is 91. So here I start at the bottom. 34.65, 91 divided 1 minus, but it should be minus, okay. And then we're just going to divide 35.37. And I have 57. Well, that's pretty large. 57.12 KSI. And then we need to do the thing where we get the F, right? So we estimate our F. It's at 91. We get that from figure 618, at least in the old book, the 10th edition. And they even have an equation for it now in the 11th edition, which is nice. And they added the top of this with megapascals, which is nice. But 91, it looks to be, I have it as 0.856, so I'll buy that. I did mine from a curve fit equation I made of my own, but 0.856. And then from that we get the A. I won't throw the numbers in there, but just as a reminder, this is what they, the form of this. But if we do that, we get 167.1, and for B, we get negative 1/3 log of FSUT over SE, and from that we get a negative 0.1104. So our estimate N for this thing is that rev divided by A raised to the 1 over B. Throw those numbers in there, and we end up getting 115,300 cycles. And I'm not reporting that yet, so I'm keeping 4 sig figs for the time being. But if I want to estimate the time, oh, by the way, no, that's not true. I actually don't get that value because I have a different thing. I should check it out. I had this stress now, so I need to put that back in there. All right, so let's see. I have my 57.12, and now divide by 167.1. Divide, and then take a 0.1104, but take the inverse of it and then raise one to the other, and I've dropped down to 16,700 cycles, and they happen every 10 seconds. So what you would do is you would go, you just have to kind of like do a little units thing where you go cycles divided by, well, I decided to go like, okay, if I have 10-second cycles, then I have 6 cycles per minute, right? Just divided 60 by the 10, and now I got cycles per minute. And so I could go 6, and then cycles per minute would give me the number of minutes, but I would rather go 60 minutes per hour, and that gives me the number of hours, maybe, I don't know. So divide that by 6 and by 60, and now I have 46.4 hours. So I don't know. I think the problem might have asked for days, so we might want to divide that by 24, and I get 1.9 days. So that would be my answer, right? Only 2 sig figs. Everything up above is too much, and even then, I might even just go 1 sig fig and say, I estimate it's going to last 2 days. By the way, with the previous lack of torque on there, it was actually 13 days. But let's take a look at the last part of the thing, which is to graph it out. And so this is always this is bold. gonna be bold here. Um, let's see how to use the graph paper. That's what's bold about it. Is trying to on the fly think my way through how to maximize a good looking graph here. Um, well, it's gonna be somebody over here. I guess I'm gonna go this way. And my maximum is really going to be my ultimate strength, right? So let's see. I want to go break that into sensible things here. So I need 91. I actually kind of need like 10, right? So what if I would go to 10, go there, 10, 20, 30, 40, 50, 60, 70, 80, 90. It's not really using my thing up as much. I think I could I get more usage out of it? I'm gonna stick with this. Okay, so here's gonna be my 90, right? So I'll label them. My old professor in machine design, there was like a kind of a I don't know, a thing that he really emphasized was like picking the proportions of a graph to use them correctly. Um, I haven't really pushed that hard. I don't know where that skill set would be necessary come from. So anyway, this is going to be sigma m, and this is sigma a. It's sort of a lost art because we graph so much stuff in Excel, right? That we don't have to think about like how do I maximize my page space for the thing. So okay, so we're setting this up here. We have 77 as the yield, so that's somewhere up there. I'll put it in there. For the endurance strength, we got where did we get that? We got 36. So that's not really very high right there. So there's our endurance strength. For our yield, we got yield down here. Do I want yield? Yeah, I want yield here. And here we have our ultimate. So I'll start out with my Langer, which should be 45 degrees. And then I'll go to my Soderberg, which should be from here to here, from the yield strength to the endurance strength. Then I'll go for my Goodman, which should be from the ultimate to the endurance. And I'll label them Langer, Goodman. I don't know a good place to. There we go. And now I'm going to be like a little bit artsy and try to draw as best I can. And it's not going to be perfect, but what the hell. There you go. That's going to be my Gerber, like the Gerber baby. Gerber baby food. And then the last one is this ASME elliptic, and this is a hard one to do really well, but didn't do a great job. I panicked and I bailed. Let's see, like that, right? It's just like the name implies, it's supposed to be an ellipse, so it kind of has more of a steeper descent to look more like elliptical as it gets down to there. But it's an experience. The ASME one right there. Okay, and let's see. We'll plot out our point, and our point is going to be pretty much 35 and 35, right? Because we had 34.65 and 35, so 35 and 35. That's an easy one to do. So kind of like trying to find where I can. I guess I'll make a straight line over there, somewhere in there, and somewhere in here. Okay, so here is our load line. from 0 up, boom. And you can see where we cross all of these. It looks actually a little more severe than I would think it was. I mean, that looks actually pretty far away from here. I don't think I asked for this, but I do want to, like, just out of curiosity, see what these ratios are. See this one. Let's just go. I'm just going to go to the. I guess I'll just go to the good one. I'll just do the check of the good one. This line over to our point right here, and I guess I'll call that O, and I'll call that A, and I'll call that B, just this time. So I got OA is approximately, it looks like 51. And then I will say to here that we look like O, that's supposed to be an A, OB is approximately, I don't know, it's like 37. So the graphical estimate here would be, let's see, we could have OB over OA, right? Because it would be 37 over 51. All right, got 0.73. All right, so I guess it does match up, right? Because we got 0.74 right here, so as bad of a job as I might have done. And then the last one is, so let's just confirm this right here, right? So we want to see this is going through this point from the ultimate, going through the load point, and we see the intersection here. So that right there is what we're graphically estimating as the equivalently completely reverse stress. And what value did we get? We said that we had 57. Okay, I'll buy that. That's 57 maybe. That's close. This is a thick pencil, right? So it doesn't. I actually wore off the label, but it's a 0.9 pencil. All right, so there you go. There's an example similar to our homework problem, but there's other, challenges in that one because it's a weird stress concentration factor. Does that make sense, Chris? You still there?
Yeah, everything makes sense.
Okay. Yeah, and I don't think this is like terribly conceptually challenging, but just to become familiar with it, you need to go through a problem, right? And then you organize it, and it just becomes kind of a routine. Just it is very cookbooky.
Right, right.
All right. Well, we used up the time.
Okay. Yeah.
Cool. Appreciate you showing up.
Yeah, thank you. Thank you for having it.
All right. So let's see. We'll close this thing down. Is it still recording? Is it still recording? It is.